Okay, so in the previous class, I introduced the idea of the phasor, and also I introduced the idea of how you can convert, when you are analyzing an AC circuit, the derivatives or the integrals that describes the behavior of a circuit using phasors. So I want to um, recover that idea from the previous class, and let's say that we have the following circuit. Now we have a voltage source. No, let's say that this voltage source have the following voltage, Vm times the cosine of omega times t. Okay, we have a resistor. Okay, and we have an inductor, and we have also a capacitor. No, and that's it. Here is the inductor, and this is the capacitor, and this is the current of the circuit. Okay, now, um, do you remember that in the previous class we computed the voltage of the resistor? No, remember that the voltage of the resistor is equal to the resistance times the current, okay? And also we know that the voltage of the inductor is equal to the inductance value times the derivative of the current with respect to time, and the voltage of the capacitor is equal to 1 over C, that is the capacitance value, times the integral of the current with respect to time. Okay, so this is like the relationships that we have. Now imagine that I want to express the voltage and current relationships of the elements of this circuit by using phasors. So for example, for the voltage of the resistor, that is equal to the resistance times the current, I can compute the phasor of the voltage of the resistor, and I can denote that phasor by using a capital letter, VR, that is equal to the resistance times the current that passes through that resistance. And here I'm using the capital letter for I to denote the current that passes through the resistor. And I can obtain the voltage to current relationship. So we have that VR over I is equal to the resistance. Essentially, this means that the voltage over the current is equal to the resistance for this element. Okay? But what happened with the other two elements, the inductor and the capacitor? Well, there is a problem here. And the problem is that, well, the voltage of the inductor, for example, the voltage of the inductor, and let me erase this a little bit. The voltage of the inductor that depends on time is equal to the inductance times the derivative of the current with respect to time. Okay? And I will express the voltage of the inductor in phasor as follows. I can compute the phasor of the voltage of the inductor, and I will denote that by a capital uh, letter that is equal to L times the current of the capacitor with respect to time, but I want to express this as a phasor. So remember that to compute the phasor of a derivative, you need to take the phasor of the function, that in this case is the current I, and you need to multiply this by j times omega. Okay? So if I want to find the voltage to current relationship, well, I can express this as VL over I. Okay? And this is equal to L times j omega. Okay? And I can do a similar thing for the voltage of the capacitor. The voltage of the capacitor that depends on time is equal to 1 over C times the integral of the current with respect to time. And I can express all these quantities as a phasor. I can compute the phasor of the voltage of the capacitor that is equal to 1 over C, and I can compute the phasor of this integral. That, remember, that is the phasor of the function that I have, that is the current, divided by J times omega. Okay? And now, if I want to find the voltage to current relationship for this element, well, I can express this as the voltage of the capacitor over the current phasor that is equal to 1 over C times J omega. The interesting part is that remember that the voltage to current relationship for a resistance, well, it's the same resistance that we measure always in ohms. But here for the inductor and the capacitor, we have these quantities, okay? And we can say that these in fact are like a type of resistance, but these two resistance, okay, depend on the frequency, okay? So here, in order to compute this resistance, you need the value of the frequency of the circuit for both cases. And we call this an impedance, okay? The impedance, let me write it right here. Impedance, okay? So the impedance is essentially a resistance that depends on the frequency, okay? If you change the value of the frequency, well, the impedance of that element will change, okay? And this impedance is always measured in ohms, okay? So that is essentially the impedance. But these relationships are very useful because instead of working with these integrals and derivatives directly, we can convert that into impedances of these elements and solve the circuit, no? By considering that these impedance terms are resistive elements, okay? That depend on the frequency of the circuit, okay? So that is like the new concept, no? Instead of working with the derivatives or integrals, we can compute the impedance of each element and solve the circuit using algebra. We do not require the use of these integral differential equations, no? So that is like the approach that we need. And well, before we continue, let me go to the presentation. Just let me a moment. Okay. So in the presentation, we have these relationships. Now, as I mentioned before, this is the impedance of a resistance in the frequency domain. This is the impedance of the inductor, and this is the impedance of the capacitor. And well, when you basically the impedance is the voltage over the current relationship in the phasor domain, okay, or in the phasor domain or in the frequency domain. There is another concept that is called the admittance. That is essentially the reciprocal of the impedance because here we are computing the current over the voltage relationship, okay? But the admittance is essentially the reciprocal of the impedance, and this admittance has units of Siemens, okay? And we denote that by the letter S. Okay, in general, I have never encountered in my life some manufacturer that use admittance as a unit. The common way to express the impedance of a circuit is using the admittance, okay? Because it has international units that are the ohms, okay? But maybe sometime in some point in your life, you will encounter the admittance, but just remember that the admittance is essentially the reciprocal of the impedance. And the impedance is essentially a complex number, no? And the impedance can have a real part and an imaginary part. The real part is called the resistance, and the imaginary part is called the reactance. And for the case of the admittance, you have also a real and an imaginary part, where the real part is called the conductance, and the imaginary part is called the susceptance. Okay? And you can express this impedance and admittances either in a rectangular or polar form, okay? Because they are essentially complex numbers. For the case of impedances that are in series or in parallel, you can simplify circuits, okay? Similar to the resistance that you use in your previous circuit class. For instance, for the impedances that are in series, you can simplify them by just adding the values together. For the case of parallel impedances, you can use the following relationship that is essentially 1 over the first impedance plus 1 over the second impedance and so on. Okay, so these relationships apply very similar to the case of resistance, okay, that you have saw in your previous circuit class, no? And for the case of the admittance, since it is the reciprocal of the impedance, the relationships are inverted. For example, if you had admittances that are in series, you need to compute 1 over the first admittance plus 1 over the second admittance and so on. And for admittances that are in parallel, you just need to add the values together. Okay, and if you notice or if you compare these equations, you will notice that they are like inverted. For the case of the impedance that are in series, you need to add the values, but for the case of the admittance, you need to simplify them as if they were in parallel. Okay, for the case of the impedance that are in parallel, you use this relationship, but in the case of the admittance, you can only add the values together and you will obtain your your equivalent admittance in order to simplify the circuit, no, and analyze it more easily. Okay, so I think that we can make an example, no, in order to explain a little bit more clear what do we need. So let me go to my tablet in order to show you how you can solve this type of exercise. So in order to solve this type of exercises, in order to simplify a circuit using the admittances, well, we need to first know what is the frequency of our circuit. Okay, so in this exercise, we have a frequency that is equal to 50 radians over second. Okay, and the circuit that we have is the following. We have here capacitor of 2 millifarads. Okay, then we have here a resistance of 3 ohms, and we have in series a capacitor. Okay, and the capacitor has 10 millifarads, and then we have here an inductor that is 0.2 henries, and then we have here a resistance of 8 ohms. Okay, so the first step in order to simplify this circuit using the impedances, well, we need to convert all the elements to its impedance equivalent. So for example, here we have a 2 millifarad capacitor, okay? But we know that the impedance of the capacitor is equal to 1 over J times omega times C. We know the value of omega, that is 50 radians over second, and we know the value of the capacitor, that is 2 millifarads. So this is equal to 1 over J times 50 times 2 millifarads, okay? So if you compute all of that, just wait a moment. Um, Let me go here to the calculator. Just 1 second. Mm, you will have the following result. Just wait a minute, please. Leaving like okay. So this result will be equal to 1, this result will be equal to minus 10 J ohms, okay? And for the value of the resistance, we know that the impedance is the same, that is 3 ohms, okay? Here we have a 10 millifarads capacitor, and this is equal to 1 over J times omega times C. And we know the value of the omega and the capacitor, so this is equal to J times 50 times the value of the capacitor, that is 10 millifarads, and this is equal to minus 2 J ohms. And we also have the value of the inductor, no? The inductor, okay, Remember that the impedance of the inductor is equal to J times omega times L, and this is equal to J times 50 times L, that is 0.2 Henries, and this is equal to 10 times J ohms, okay? So we know, well, also I am forgetting about the impedance of the 8 ohms resistor, that is basically the same. And now I need to rewrite or redraw the circuit by considering the impedances. Okay, so to do that, we know here that we have the capacitor of 2 millifarads that is equal to minus 10 times J ohms. And here we have the resistor of 3 ohms. And we have here the capacitor of 10 millifarads, but we know that the impedance of that term is equal to minus 2 J ohms. Then we have here the inductor, and the inductor has an impedance of 10 J ohms. And here we have another resistor, and the resistor has impedance of 8 ohms. Okay? Now, we can start simplifying now the impedances. So here you can notice that we have these two elements in series. So I can simplify this, but also these two impedances are in series. So I can add them together only, no? That would be the equivalent impedance. So I will rewrite this as follows. I will have here minus 10 J ohms, and I will simplify these two elements that are in series. So I can rewrite this impedance as follows. Here we have a value of 3 ohms minus 2 J ohms. And if I simplify these two elements, I will have something like, just a moment, 8 J ohms plus 8 ohms. Okay? So this is like the equivalent impedance between these two elements that are in series, and also these two elements are in series. Now that I have redrawn the circuit, now I can show you which elements are in parallel. So here we have one element in parallel, and here we have another element in parallel. Okay, remember that for a parallel connection, the two elements needs to have two nodes in common. So here, this is a node because we have a connection between elements, but also this is a node. But this element right here and this element right here are sharing two nodes. So since they are sharing two nodes, we can say that they are in parallel. So in order to compute the equivalent impedance between these two parallel elements, okay, we can use the relationship that we saw earlier. So the impedance, well, the equivalent impedances between 3 ohms minus 2 J ohms that are in parallel with 10 J ohms plus 8 ohms is equal to 1 over 1 over 10 J ohms plus 8 ohms plus 1 over 3 ohms minus 2 J ohms. And this is equal to, if you make all this operation in your calculator, you will obtain the following value. That will be equal to 3.2216 minus 1.0702 J ohms. Okay? So this is a complex number. I am expressing this in rectangular form. And now this is the equivalent impedances of these two elements that are in parallel. Okay. Now I can redraw the circuit again. Okay. Here we have the capacitor that has an impedance of minus 10 J ohms. And here we have the equivalent impedance. Okay. And this equivalent impedance, okay, is the result of simplifying these two impedances that are in parallel. And we know that value is right here. No? This is equal to 3.2216 minus 1.0702 J ohms. Okay? And well, if you notice, these two elements are in series. Okay? So I can simplify this further. In fact, I know that the equivalent impedance of the circuit will be equal to minus 10 J ohms plus the equivalent impedance, no, that is equal to 10 J ohms plus 3.2216 minus 1.0702 J ohms. You add all these values together. You can use your calculator for that. And you will obtain a value that is equal to, um, well, I am missing something here. Well, a minus sign right here. So this is equal to the equivalent impedance of all the circuit is equal to 3.2216 minus 11.0702 J ohms. And this is the result. Okay. And that's it. Now we have finished the exercise. Okay, so this is a brief introduction into impedance analysis. So I hope that you like this video. And if you have a question, you can tell me what do you think about this procedure. Okay, so thank you for watching and see you later.